Good afternoon, everyone. I'm Jailbeck from Princeton University. I'm truly honored to have this opportunity to present our work here. Today, I'd like to introduce an extreme performance point-of-load converter for high current microprocessors. The data center industry in the United States consumes 90 billion kilowatt-hours of electricity a year. The amount of carbon dioxide generated due to this amount of electricity is equivalent to the carbon dioxide emitted by the entire American airline industry. On a global scale, data centers consume 416 billion kilowatt-hours of electricity a year. These numbers are only expected to grow in the near future. It's clear that data center energy usage is a large and expanding problem. In this presentation, let's focus on the power delivery from the AC/DC power supply to microprocessors. Traditional data center power architecture uses 12-volt busbar, but as the power consumption of microprocessors has significantly increased, a 48-volt power architecture is getting more spotlighted. The greatest advantage of 48-volt power architecture is that it can improve power delivery efficiency. However, 48-volt architecture still has challenges. Point-of-load converter of 48-volt power architecture should have 4 times higher voltage conversion ratio compared to the traditional 12-volt architecture. Also, it should satisfy high upper current and high bandwidth requirements. These requirements make it difficult for 48-volt PoL converter to achieve high efficiency and high power density. In order to solve these challenges, many researchers have studied two-stage approaches, such as LLC plus buck design and hybrid switched capacitor plus buck design. In this presentation, I'd like to introduce a merged two-stage approach which can give us higher efficiency and higher power density compared to traditional two-stage approaches. This figure shows a block diagram of the traditional two-stage approach. First stage is an unregulated stage. A decoupling capacitor decouples 2 stages. And then existing state-of-the-art multi-phase buck stage of 12-volt power architecture regulates the output voltage with high control bandwidth. To make this approach useful, a key point is that the unregulated stage should have high conversion efficiency around 99% and high power density. There are 2 popular topologies for the unregulated stage. One is transformer-based design such as LS resonant converter. It has low component count due to a transformer. This design has low write-load efficiency and low power density. The other topology is hybrid switched capacitor-based design, such as switched tank converter. This topology is very attractive because of its transformer-free design, high write-load efficiency, and high power density. However, its additional resonant inductor and large decoupling capacitor of two-stage approaches limit higher efficiency and higher power density. As a result, we still need more efficient way to improve 48-volt PoL converter efficiency and power density. In this presentation, I'd like to introduce a merged two-stage Lego pro architecture. Here you can see one sub-module of the merged two-stage Lego pro architecture, which is composed of 1 2-to-1 switched capacitor unit and 1 multi-phase buck unit. With this structure, we can achieve many desirable advantages. First, Lego pro architecture does not require resonant inductors for soft charging operation. Second, it eliminates large size of decoupling capacitor to merge the operation of 2 stages. So buck units uses switched capacitor CF1 and CF2 as its input capacitors. Third, by merging 2-stage operations, buck inductor can be used as current sources for the switched capacitor unit. In the switched tank converter, resonant inductor is connected with capacitor. On the other hand, buck inductor is used in Lego pro converter to achieve soft charging operation. Also, it can leverage GCS operation and scale wave current. As a result, switched capacitor stage can effectively reduce switching frequency and capacitor size. And Lego pro architecture can use the existing state-of-the-art buck converter for high control bandwidth. Lego pro architecture is scalable and modular, so it's very attractive for ultra-high current microprocessors. One merged two-stage cell module, as you can see in this figure, can be linearly extended like a Lego block. and each module operates as a group with the same control signal. This is why we named our architecture as LEGO. To cover high input voltage and high output current, firstly, we can connect N switched capacitor unit in series. So we can split high input voltage into N low voltage domains. Then N buck units can be connected in parallel, which divides high output current into N low current path. With this configuration, LEGO Pro architecture can reduce switch voltage stress, switch current stress, and buck inductor size. Moreover, N split input voltages are automatically balanced by the parallel connected buck units. And N divided output currents are also automatically shared by the series connected switched capacitor unit. This slide shows an example of 48 volt to 1.5 volt 300 amp LEGO Pro converter design for high current microprocessors. We stacked 3 sub-modules as you can see in the left-hand side figure. 3221 switched capacitor units convert 48 volt high input voltage to 8 volt low voltage. And 1 4-phase buck units handles 100 amp output current, so each inductor has 25 amp maximum current rating. 3 series connected switched capacitor units group operate with the same 50% complementary gate signal at lower switching frequency. And 3 parallel connected 4-phase buck units are designed with interleaving operation at higher switching frequency. Let me explain hardware implementation and experimental setup of LEGO Pro converter in this slide. Left-hand side figure shows a prototype with 577 watt per cubic inch power density. We use the digital controller and mimic the CPU with resistor load and CPU heatsink. For switched capacitor unit, we use silicon MOSFET, 45 microfarad effective capacitance, and 125 kHz switching frequency. For base buck units were designed with DRMOS, 1 microhenry inductor, and 500 kHz switching frequency. Right-hand side figure shows a picture of experimental setup. To measure the efficiency accurately, we used age-length multimeters and chroma electronic loads. This slide shows experimental results. Above left figure shows captured startup operation of LEGO Pro converter. Output currents of 3 buck modules are unbalanced at the starting point, but they are automatically balanced by the topology characteristic. As shown in below left figure, LEGO Pro converter has quite largely poor at buck input voltage because we removed large size of the decoupling capacitor. But it well regulates 1.5 volt output voltage and 300 amp output current. Right-hand side figure shows measured efficiency and loss distribution of LEGO Pro converter. LEGO Pro converter achieved 95.8% peak efficiency with 45 microfarad effective capacitance, and 96% efficiency with 90 microfarad effective capacitance. Calculated peak efficiency of each stage is 99.5% and 96.3%. Major loss around 90% comes from the buck stage, as you can see in this figure. So by improving the state-of-the-art buck stage efficiency, LEGO Pro converter can be much more efficient. Summary. In this presentation, we proposed high efficiency and high power density merged two-stage LEGO Pro architecture. LEGO Pro architecture eliminates resonant inductor of hybrid switched capacitor design and removes large size of decoupling capacitor of traditional two-stage design. By merging two-stage operation, LEGO Pro architecture is able to achieve soft charging operation, soft switching operation, and automatic input voltage and output current balancing characteristics. With linear extendable and group operated characteristic, LEGO Pro architecture is able to cover a wide range of applications. Also, we showed a design example of 48 volt to 1.5 volt 300 amp prototype for CPU power supply. In this design example, we stacked 3 sub-modules and achieved 96% peak efficiency and 577 watt per cubic inch power density. In summary, we propose extreme performance miniaturized point-of-load converters for high current microprocessors. Thank you for your listening.
Muted.
Hello everyone, here is Jayo. Thank you for joining, and please feel free to post your questions. As mentioned in the presentation, future microprocessors such as CPU, GPU, and TPU will consume higher and higher energies, which requires point-of-load converter to deliver very high up current. Yesterday, NVIDIA announced high-performance 7-nanometer GPU, Ampere GA100, and Bicore's point-of-load converter supplies 750 amp continuous current and 1,200 LT current. High current microprocessor is not far from us, and it is already in us. And I believe our architecture allows us to supply high current to microprocessor with high efficiency and high power density and high control bandwidth. Oh, yeah. So there is a question about, oh, yeah. So this efficiency number does not include gate drive loss, and it just includes the power conversion efficiency. To measure the 300 amp of current, we use just with the chroma electric load current, and the chroma electric load current display error is just 0.5%. So we use that displayed number to measure the efficiency. Another question is about TwoStage diarmoses. We use the diarmos from the BSHI, and so and power density is measured just considering the power component and power stage. We didn't consider the gate driving area and any other control components. Another question is about dynamic performance of this architecture to low step. As I mentioned before, we used state-of-the-art bulk converter. So as the performance of the state-of-the-art bulk converters, we can also achieve the same performance of the state-of-the-art bulk converter. That's the big advantage of our architecture. And another question is about how do you balance the input voltage during startup and input voltage transient. So actually, you can see our APEC papers. We analyzed the architecture operation with the large signal modeling, and with the large signal modeling, it is automatically balanced, and the parallel connected buck units can give us input voltage sharing, and the series connected switched capacitor stage can give us automatic current sharing operation. Okay, I think we are running out of time. I'm happy to introduce our work and discuss with you. If you have any questions and comments, you can send me an email, or we can set a virtual chat. Thank you for joining, and please enjoy your rest of OCP conference. Thank you.